Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So in this video, I'm going to discuss solutions to another 5 sets of problems on friction. And I hope that for this series of 5 problems, you will learn another technique on analyzing problems involving friction. So level 16 problems. The 100 Newton block hangs from a cable as shown. Pulley C is connected by a short link to block E, which rests on a horizontal rail. Knowing that the coefficient of static friction between block E and the rail is mu sub s equals 0.35, and neglecting the weight of block E and the friction in the pulleys, determine the maximum allowable value of data if the system is to remain in equilibrium. So, meaning determine the maximum allowable value of data means that we allow the body, the block, to undergo impending motion. So, the maximum frictional resistance, which is coefficient of static friction times normal, applies in this problem. So for the solution, so we have to draw the free body diagram. You have to apply the tension here. So 100 divided by 2, so each tension here would be 50 newtons as shown. Then this is also 50 newtons. Then we draw the free body diagram of this upper part as shown. So transmit the 50 Newton force tension. Then this is also 50 newtons. Then let's have the normal reaction under E. Then friction, which is supposedly going to the left opposite to 50. This inclined 50 Newton tension. Then we sum up forces normal to have expression for the normal reaction at E. So normal at E equals 50 plus 50 plus 50 cosine of theta. So N sub E is equal to 100 plus 50 cosine of theta. Then we sum up forces horizontal. So 50 sine of theta minus F equals 0. So that means F is 50 sine theta. And F is coefficient of static friction 0.35 times normal at E. So 50 sine theta, and F is F max, which is equal to 0.35 times normal at E, 100 plus 50 cosine theta equals 50 sine of theta. So F should be equal to F max because we are computing for the maximum allowable value of theta to cause impending motion of this block E here. So simplifying and using the calculator or by trial and error, so theta max, which is equal to 60.64 degrees. Level 17, the 10 kilogram block is attached to link AB and rests on a moving belt, knowing that coefficient of static friction is 0.3 and coefficient of kinetic friction 0.25, and neglecting the weight of the link, determine the magnitude of the horizontal force P that should be applied to the belt to maintain its motion to the left as shown and to the right. So the condition is the determination of the magnitude of the horizontal force P that should be applied to the belt to maintain its motion. So meaning to say the belt will have motion, constant motion. So therefore, the maximum frictional resistance is mu sub k times the normal. So to draw the figure. This is the given figure, by the way. So for the solution, let's have apply the weight, which is 10 times 9.81. Then the normal reaction here, which is equal to Na. This is the normal reaction on the underside of the belt. Then we have the effect on the link AB, which is, let's denote it by Q, tension Q, because friction should be in this direction, underside. It's either left or right, but we expect that it should be to the left for the case where we have uh, motion of the belt to the left. So it should be, the effect should be to the left also on the underside. Then we sum up forces normal equals 0. So Na equals 10 times 9.31 plus Q sine of 35 degrees. So Na is equal to 98.1 plus Q sine of 35 degrees. Then for the FBD of the block and the forces associated with the free body diagram, summation forces horizontal equals 0. So F is equal to Q cosine of 35. The component of Q is Q cosine 35, or Q cosine 35 degrees is equal to F. Since F is F max kinetic, which is 0.25 times normal, so we draw the free body diagram of the belt. Then this time we have the surface in contact with the underside of the block. So by action reaction, we have F Na down, then F, which was previously assumed to be leftward, is now rightward, and we now involve P. So summation forces horizontal, that means P equals F, and F is 0.25 of normal A, 98.1 plus Q sine 35 degrees is equal to Q cosine of 35 degrees. So this is F, coefficient of F max kinetic, which is mu sub k times normal at A, then equals Q cosine 35 degrees. From here, we can solve for Q. So Q is equal to 36.29 newtons. So from this free body diagram, P equals F. So where F is Fk max equals P, so 36.29 times, so Q cosine 35, 36.29 cosine of 35 degrees. So P is equal to 29.73 newtons. For part B, so here is the free body diagram. Then we have the force P to the right this time. Then we have the effect of pulling the belt rightward is to have this reaction on the link AB, Q to up to the left to oppose that force P. Then normal at A, then the weight friction, which is this time to the right on the underside of the belt, and Na equals 10 times 9.81, then minus Q sine for 35 degrees this time because Q is up to the left. Then F is equal to Q cosine of 35 degrees, and this is also Fk max, so 0.25 of normal at A, 98.1 minus Q sine 35 degrees equals Q cosine of 35 degrees. Solving for Q, Q is 25.48 newtons. Having found Q, we can now solve for F, and F is also equal to P. F is F max kinetic, and it is Q cosine 35. So this is the free body diagram, so that's why P is equal to F, and F is equal to Fk max. So F equals Fk max equals P equals 25.48 cosine of 35 degrees. So solving for P, P is equal to 20.87 newtons. So that's it for this problem. Level 18, knowing that P is 100 newtons, determine the range of values of theta for which equilibrium of the 7.5 kilogram block is maintained. So we are talking here of the range of values of theta, so it should be the minimum value and the maximum value. From that fact or requirement, that means that we allow the block to have impending motion, and therefore the maximum frictional resistance is that by statics mu sub s times normal. So this is P. So we have the weight, which is 7.5. For the solution, we have the weight, which is 7.5 times 9.81. Then we have P, which is equal to 100 newtons given. Then the normal reaction here, FBD, then friction, which is either up or down depending on which angle we compute. So if it is minimum angle, then the value of the direction of F max, which is mu sub s times normal, should be upward for minimum theta, so that it will help the vertical component of 100, which is smaller if theta is small also. So for minimum theta, friction should be upward, so that summation forces horizontal to solve for the normal reaction on the wall. So normal reaction on the wall equals 100 cosine of theta. Then for the equation, summation forces y equals 0. So we have 100 sine of theta plus f equals 7.5 times 9.81. So f is mu sub s 0.45 times nw, and the value of theta here corresponds to the minimum theta as mentioned earlier to anticipate. So 100 sine theta plus 0.45 of quantity 100 cosine theta equals 73.575, 7.5 times 9.81. So simplifying, 100 sine theta plus 45 cosine theta equals 73.575. So you can express cosine theta as square root of 1 minus sine square theta for the algebraic calculations, or you can use your calculator, high-tech calculator, to evaluate this numerical equation for theta, or by trial and error. So solving for theta by trial and error, theta is equal to 17.91 degrees, or actually we solve for theta by the high-tech calculator, which can generate the solution to this equation here. So it is 17.91 degrees for minimum theta. For maximum theta, because it is maximum, the angle P here is pointing up to the left, but theta is maximum, therefore this time friction max is going down, and therefore the equation summation forces vertical is 100 sine of theta minus friction, which is now downward, minus or equals 7.5 times 9.81. So substitute the value of f, which is again 0.45 times 100 cosine theta. So 100 sine theta minus 45 cosine theta, which is this value here, equals 73.575. Again, by trial and error or using your high-tech calculator, the maximum value of theta is 66.37 degrees. Therefore, for the final answer, 17.91 degrees is less than equal to theta, and theta is less than equal to 66.37 degrees. So this is the range of values of theta that makes the system in equilibrium. level 19, the 250 Newton block A and the 100 Newton block B are supported by an incline that is held in the position shown. Knowing that the coefficient of static friction is 0.15 between all surfaces of contact, determine the value of data for which motion is impending. So again, motion is impending, so we use the coefficient of static friction 0.15 in computing the maximum frictional resistance. Since A is heavier than B and they are only attached to this one cord, so A will definitely moves downward while B is upward. So if A moves downward, if we draw the free body diagram for the solution, then the frictional resistance should be up as shown in the free body diagram. So this is the FBD of the upper block because we expect that A will slide down, so friction would be going up. So normal is of course perpendicular to the incline in A underside of A, and friction is up to the right as shown. So we will call this the normal axis, the tangential axis along T, and the angle here is angle between the normal and the vertical. By principle is also the angle of inclination. So friction is up to the right, FA, then remember that FA is maximum mu sub S times NA. So then for the lower free body diagram, let's transmit these forces here underside to the lower FBD. So FA is now going down because by action-reaction principle, this is NA, the weight of block B is 125 newtons, and this angle is also theta. So we have a normal reaction at B as shown, then friction because B is going up, moving upward as expected. They should have opposite motion, so friction should be going down, and that is equal to F sub B as shown, and FB is also maximum mu sub S times normal at B. So for FBDA, summation versus normal equals 0, NA equals to 50 cosine of theta. Then summation versus tangential, FA plus tension equals 250 sine theta. FA plus tension equals 250 sine of theta. So that's it. FA times tension equals 250 sine of theta. So then for the lower free body diagram, or substituting the value of FA, which is equal to 0.15 times NA, so we have 0.15 times 250 cosine theta plus tension equals 250 sine of theta. Solving for T in terms of these terms, T is 250 sine theta minus 37.5 cosine theta. So take note that this 37.5 cosine theta is equal to FA. So in the second, in this lower free body diagram, summation forces tangential equals 0. So tension equals FA plus FB plus the tangential component of 125 sine of theta as shown in the figure. So remember that FA is 37.5 cosine theta. Then we need to express FB in terms of the normal NB, and to do that, summation versus normal equals 0 for this FBD. So NB equals NA plus 125 cosine theta. Substitute the value of NA, which is equal to 250 cosine theta. So NB is 250 cosine theta plus 125 cosine theta. So NB is 375 cosine of theta. From there, we substitute the value of T, which is, so FB is 0.15 times NB. FB is equal to 56.25 cosine theta. So substitute into this equation the value of T, which is 250 sine theta minus 37.5 cosine theta, then equals FA. FA is 37.5 cosine theta. FB is 56.25 cosine theta, then plus 125 sine theta. Combining like terms, 250 sine theta minus 125 sine theta is 125 sine theta in the left side. On the right side, 37.5 cosine theta plus 37.5 cosine theta, 75 plus 56.25 cosine theta. So 125 sine theta equals 131.25 cosine theta on the right side. So that tangent of theta is equal to 131.25 over 125. So from there, we can now solve for the value of theta for which motion is impending, and this corresponds to the maximum angle of inclination of the system to cause impending motion of the system. So theta equals 46.4 degrees. So, for the last problem of this series, level 20, three 4-kilogram packages A, B, and C are placed on a conveyor belt that is at rest. Between the belt and both packages A and C, the coefficients of friction are mu sub s 0.3 and mu sub k 0.2. Between package B and the belt, the coefficients are mu sub s 0.1 and mu sub k 0.08. The packages are placed on the belt so that they are in contact with each other and at rest. So determine which, if any, of the packages will move and the friction force acting on each package. So here is the given figure, and for the solution, let's have the free body diagram of package C as shown in the figure. Then we have to apply the weight, which is 4 times 9.81, superimpose the normal and the tangential axis as shown. Then we have the angle here, which is equal to 15 degrees angle of inclination. So this is also 15 degrees between the normal and the vertical. And then we have the normal at C, package C. Friction, which is up to the right, because the only possible motion of this package is going down. All the three packages, if in motion, possibly would be going down. So friction should be opposite, going up. Call that F sub C. Then we have, if this is in motion, then there will be contact force between package C and the next package, which is package B, and we will call that P1. We will determine P1 later. So let's transmit P1 to the next package B, and we have to apply the weight, which is 4 times 9.81, superimpose the normal and the tangential axis, and then we have the normal reaction at B and B, and friction, which is up to the right, we will call that FB. And if this angle is 15 degrees, and if B slides, then it will again transmit reaction to the next package, which is A, and we will call that P sub 2. Then let's have the package A free body diagram. Then superimpose the normal and the tangential axis. Then we have normal reaction at A. Then we have the friction, which is F sub A up to the right, and weight 4 times 9.81, then the angle 15 degrees. So first for package C, summation forces normal equals 0. So N sub C is equal to 4 times 9.81 cosine of 15 degrees. So summation forces normal from this FBD here, N sub C is 4 times 9.21 cosine of 15 degrees. So N sub C is equal to 37.903 newtons. And take note that because each package has the same weight, then same normal reaction. So this is also equal to N sub B and N sub A. Then let's compute for F sub C required for package C to be in equilibrium as shown. So F sub C minus 4 times 9.81 sine of 15 degrees equals 0. So assuming P1 is 0 yet. So F sub C is equal to 10.16 newtons. Then let's evaluate the maximum frictional resistance under block C or package C, which is coefficient of static friction 0.3 times normals at C. So FC max is 0.3 times 37.903 newtons, and that is equal to 11.37 newtons. Since the maximum frictional resistance under package C is 10.16 newtons for package D to remain in equilibrium, the maximum frictional resistance is higher, 11.37 newtons. Resistance to motion of this package C here, resistance to slipping or sliding. Therefore, the package C is in equilibrium because F sub C, which is 10.16 newtons, is less than 11.37 newtons. So for our conclusion, so P1 is 0 here because package C is in equilibrium. FC or package C is in equilibrium. Package C is at rest, therefore F sub C is 10.16 newtons. So P1 is 0, so this has no value. Then we next investigate package B. So for package B, F sub B minus 4 times 9.81 sine of 15 degrees equals 0. Again, we don't treat P2 yet. So FB is equal to 10.16 newtons, just like for package B to remain at rest. Then the maximum frictional resistance under package B is coefficient of static friction, which is 0.1 times normal at B. And this time, 0.1 times 37.903 is only 3.790 newtons. Since the frictional resistance under B for package B to remain at rest is 10.16 newtons, the maximum frictional resistance under B is only 3.79 newtons, so that means package B slides. So because package B slides, by principle, if it slides, the maximum frictional resistance that can develop is coefficient of static friction 0.08 times normal, which is 37.903. So FB is 10.16 newtons greater than 3 points FB max. So conclusion, package B moves, and because it moves, by principle, the maximum frictional resistance under package B is that of coefficient of kinetic friction times normal at B. So 0.08 times 37.903 newtons equals 3.032 newtons. So for our answer, package B moves and FB is equal to 3.032 newtons. Then we solve for P2 because P2, which is the force that will be transmitted to package A, because B is moving downward. So summation forces tangential equals 0. So P sub 2 plus FB, which is 3.032, equals 4 times 9.81 sine of 15 degrees. So P sub 2 is equal to 7.124 newtons. Then let's investigate package A from the figure. So FA minus 4 times 9.81 sine of 15 degrees minus P2, which is 7.124, equals 0. So the frictional resistance or friction that under package A that must develop so that this remains at rest is equal to 17.28 newtons. So that is required so that package A will be in equilibrium. But the maximum frictional resistance under package A is mu sub SA, which is 0.3 times normal at A, which is 37.903. And that is equal to 11.37 newtons again, because 17.28 newtons is greater than 11.37 newtons. So that means package A moves. Because it moves, by principle, again, the maximum frictional resistance that can develop under moving body is coefficient of kinetic friction 0.2 times normal at A. So FA is 17.28 newtons greater than 11.37 newtons. So that's why package A moves. And because it moves, by principle, the maximum frictional resistance is coefficient of kinetic friction 0.2 times normal, 37.903. So FA is 7.581 newtons. So for the final answer, package A moves and FA is 7.581 newtons. So that's it, and I hope that you were able to follow, understand the explanations, and hopefully with so many problems, some are almost similar, you can gain experience and hopefully be confident in solving problems on friction.